So Mike, if you want to come up and talk, Mike's going to give the first part of the presentation, and I'm going to do a little segment about some specific things on the moon that you can look at that I thought were interesting.
You know, as Steve mentioned, I had the same sort of attitude, and I don't want to repeat everything he said, but I looked at the moon more as a, you know, as a hindrance, and I planned my outings of observing around the moon when the moon wasn't going to be around. And it was probably a few months before we started the observing program that I started to take more of an interest in the moon. I got myself a moon chart, and I started to spend a little more time. And as Steve had also mentioned, you know, it gives you more opportunities to get out under the night sky, and it's really very gratifying because the more the more you delve into it, the more you can, more features you find, the more kind of different kind of geologic structures on the moon. It's actually very interesting. So, you know, I kind of struggled tonight what to talk about. I didn't want to talk about just observing because I haven't really been observing that long, and I'm not an expert in astronomy or on the moon in general. So I decided on the topic, you know, where did the moon come from? It was a question I had in my mind that I didn't know the answer to, so it gave me an opportunity to kind of learn a little bit about this. Just for your own purposes, this picture has nothing to do with the presentation. I like the picture. This is actually a picture from the very first science fiction movie ever made in 1902. All right, it was called A Trip to the Moon. You can actually find it on YouTube. It's only about 12 or 13 minutes long. It's actually quite funny. They didn't have the movie thing down at that point, so it really looks like a vaudeville show. And it has a lot of the stereotypes from that time period. So it's actually quite it was quite funny when I watched it. But if we think about the moon, you know, in our mythology, the moon was very important, okay, to people on Earth. It was used to mark time. It was used to mark changes, and it was also, you know, its repetitive cycles. Okay, so many cultures in the past used it to mark time. Even today, some cultures use it to mark time. Some would argue that it's better than the current system that we have. Is that if we did the lunar cycles, our calendars would be more accurate. Okay? But if we look around the world, you know, the Aztecs and the Maori, very different parts of the world, one in South America, one in New Zealand, had the same traditions of the moon actually being associated with death, right? And that the moon was actually coming to collect souls. The early Greeks and early Hindus thought it was a place where the dead went. Okay? When, especially the Hindus, where they believed in reincarnation, they felt the souls went to the moon, you know, to wait for their next assignment before they came back to Earth. Okay? And then in the Roman times, they had a moon goddess named Luna. And that's where we get the lunar, the word today, right? It comes from Latin, from the Romans. And in Chinese history, there's a major festival, even today, in China. The second most important festival, besides the Chinese New Year, is what's called the Mid-Autumn Festival. Okay? It takes place in September. Okay? And it's a veneration of a from a myth of a goddess of the moon that was really there after saving the world from unscrupulous people. And they still celebrate this every year. It's a very important holiday. Families get together, they have dinner, they eat these little pastries called moon cakes. Some of them are actually quite good, especially the fruit ones. There's a savory one that has a cooked egg yolk in the middle of it. It's kind of, the fruit ones are kind of nice, but then they go out and look at the moon. And what they do is think of their family that they're not with. And people all over the country, they feel they have a connection because they're all looking at the moon at the same time. So they may have a relative on the other side of the country, but they're both looking at the moon at the same time, and they have this connection. So the moon's been very important, in our culture. But we're not going to talk about mythology. We're going to talk a little bit more about, a little more on the science side of it. So we're going to start with a guy called Anaxagoras. Okay, and he was a Greek. A pre-Socratic Greek, okay? What that means is before Socrates. It was a very early Greek philosopher. And what they felt was that they wanted to explain phenomena by natural law rather than by the action of the gods, okay? So it was kind of that first step into science and looking at things and saying, this needs to be a logical explanation for what's happening here. So he's one of the first. to realize that the moon was illuminated by the sun. And by having that insight, he was able to, the first person to accurately explain eclipses and the phases of the moon. Okay, so this is going all the way back. This was 5th century BC, so mid 400s BC, that Anaxagoras was active. So he hypothesized that the moon was just a rock that was flung off from the Earth. You know, that was his explanation of where the moon came from. The sun he thought was a fiery rock. Okay, so he had that image of fire, right? So he had a rock being the moon and a fire rock, and then he thought the stars were very small fiery stones. Okay, and that's kind of what he was thinking. And again, 5th century BC. And because of this, he was exiled, okay, toward the end of his life and sent back, you know, to his home in Ionia, because he said that the Earth, the moon and the sun were not deities. You know, we're not part of the gods, right? And that, again, that's part of that, as I mentioned, the pre-Socratic attitude of using natural law to explain these things. Well, this went on, you know, about 100 years after this gentleman, a person by the name of Eudoxus, okay, came up with the theory that the Earth was the center of the universe and that the moon and the sun and all the planets were actually crystalline spheres, concentric spheres that surrounded each other, and that's how the universe was made up. It was that, you know, geocentric or Earth-centered universe. And, you know, Aristotle after him kind of added to that, and then even Ptolemy in the early 2nd century AD, you know, put a system together, you know, for that as well. And that system persisted for almost 2,000 years. Okay? For almost 2,000 years, this was the kind of worldview of the universe, okay? And it wasn't until the Renaissance, you know, with Copernicus, and Kepler, and Galileo, that we started to see something happen a little bit differently. And even up to that time, they were really only trying to explain the observations, trying to explain what we were seeing. We're seeing motion, right? We're seeing the planets move in certain ways. We're seeing the moon. How do we explain it? So there wasn't really a lot of thought going into, you know, how this began and how it formed, but more of we're just explaining what we're seeing. Okay. Once that was completed, okay, once they were able to explain, again with the theories of Copernicus, when we moved to the heliocentric or sun-centered model, you know, that's when, okay, we could explain and we could track and we could very accurately tell you where the planets were going to be, when there were going to be eclipses, and really be able to, you know, set the calendars based on what we see in the stars. Then the thought started turning to, okay, how did this stuff form? How did we get here? Okay, and that brings us, you know, to the early 19th century. Okay, 18th century. So very famous person, Pierre-Simon Laplace. I know we have a lot of engineers, science people in here, right? Laplace transforms, right? Stuff of your nightmares. You know? But not only was he a mathematician, he was also a noted physicist and astronomer. But you can see I've actually added down the bottom here, just in case you find any stray differential equations around tonight that need to be solved. We've got a Laplace transform here for you to use. So always trying to be helpful. Okay. So Laplace, you know, developed what was called binary accretion theory or accretion theory. Okay, and what that started, you know, with a Swedish philosopher back in 1735, actually introduced the idea that the solar system was formed by accretion, you know, dust and gas swirling and consolidating. And then Laplace in 1796 expanded upon that and developed it further. And his theory was that the solar system was formed from this condensing gas and dust. And unfortunately, he was essentially correct, but he couldn't prove it at the time, right? We didn't have the scientific methods to be able to say that was definitely what was happening. And it kind of fell out of favor in the 19th century and the 20th century. And people kind of, you know, put that down for a little bit. Okay? So that was just to get the timing. So binary accretion theory, you know, just around 1800, okay, is when that became known. Then in 1879, George Darwin came up with a different theory. George Darwin, by the way, was son of the famous biologist Charles Darwin. he was a lawyer, a geologist, and an astronomer. And it was through his knowledge of geology that he developed what was called the fission theory. Okay, in the early days, Earth was not what we see it today, right? In the literature, they like to call it a proto-Earth. So it wasn't the solid Earth we see. It was a mixture of liquids and rocks and gases in this, in this swirling solar system as it was forming. And so his theory was that this was spinning so fast that it caused a bulge in the equatorial area. And that bulge became so big that finally a piece just broke off, okay, and stayed within the Earth's orbit. And that's how, and that's how the moon was formed. It was taken from a piece of the Earth and it was put out there. And that was the theory of George Darwin, right? And then there was a third theory, okay? It was called the capture theory, okay? First put forth by Thomas Jefferson Jackson C in 1909, okay? And what he postulated was that the moon was from a different part of the solar system and got captured in the Earth's gravitational, by the Earth's gravitational pull and was captured by the Earth. Now, by the way, he was a very colorful character, this Thomas Jefferson Jackson C. This is having such a long name. He was the bad boy of astronomy in the late 1800s. He was fired from several jobs. He worked for Lunar Observatory, got fired from there, came in conflict with almost everybody he had relationships with. He's mostly known because everything he's ever put forward in physics and astronomy was wrong. And it was true. He was very arrogant, so he didn't play well with others, and he was also very careless in his scientific method, and that got him into a lot of trouble. I mean, he actually even had to have, he was banned from publishing in the Astronomical journal. He published a paper on variable stars. That was kind of his thing. And another scientist, in a later paper, refuted, in a scientific way, refuted what he had put down in his paper. And apparently he wrote a very nasty and abusive letter to the Astronomical journal. And at that point, they banned him. They banned him, right? So basically, cancel culture's been around for a long time, right? Especially with certain people, right? So a very colorful character. I mean, he bounced from place to place. He taught at the Naval Academy, I think, for one semester. And the Navy transferred him to some obscure shipyard and made him the head of the time station. And he just stayed there for the rest of his career. He still wrote things and inflamed people. He actually had a very vitriolic argument with to Einstein and his theory of relativity, which was basically, by this time, everybody was just ignoring him, right? But he had this third theory, and this is probably the only one that actually captured some, captured some attention, from other scientists as a possibility. So this is what we have. We have these three theories, right? We have the accretion theory, we have the fission theory, and we have the capture theory. So which one is correct? Both had pros and cons, right? And some of the things, binary accretion theory, some thought that the moon and the Earth were way too different, right, to actually have been formed at the exact same time through accretion. In fission theory, in later days, I think it was the 1930s or so, advances in fluid dynamics kind of proved that the Earth couldn't spin that fast enough that you could throw off material. A bulge that formed in the liquid like that would actually act as a braking mechanism, right, and slow the Earth back down. So there was some, takeaways to that. And in capture theory, the thoughts were that the velocities would be too great. If bodies moving through the solar system, the velocity would be too great for gravitation to actually take over. It would overcome the gravitation. So, these things, that's the wrong way. Okay, my presentation has stopped working. All right, I'm at a bit of a loss here, but. Okay, anyway, I'll continue. So these debates continued all the way up into the 1960s. Okay, there were pros and there were cons. Even and they were updated. Like in the 1950s, some scientists actually were advocating back for the capture theory. Okay, because they felt that that possibly this other body was in a close orbit with Earth, and that it gradually, over a long period of time, kind of caught up with Earth and then ended up being captured into its gravitational orbit. Okay, so these went on until the 1960s, and one of the main, one of the main missions of NASA, and in the way they collected their samples, was in fact to try to confirm one of these three theories. Okay, to try to find out which one was correct.
This is not the.
Yeah, that's Steve's presentation.
So mine might be better.
Mic drop.
The computer is doing some weird thing. It's like,
Of course it is.
yeah, all right, where you move come from, all right, so we'll go back. Now, yeah, that's it.
So anyway, part of the Apollo mission. So that's why they landed and they took samples in many different places. Okay, around the around the moon, because they wanted to do the analysis and find out who was correct. Okay, and so several years after the Apollo missions, there we go. Okay. Okay.
Maybe you need to take his thing out.
All right, so this is what we talked about this. All right, no, we're using the PDF. Okay. So in 1974, two scientists were looking at all of this data collected from NASA, and they came up with a completely different theory. They came up with the giant impactor hypothesis. Okay. Now this was not exactly brand new. This actually came up in 1946 by a scientist named Reginald Daly, and he was using it to refute the fission theory. Instead of saying a piece was pulled off of Earth and hurled out, he said something hit it and knocked it out. Okay, but it was not given a lot of, because we didn't have the tools to prove it at that point. So it was kind of pushed to the side. But after looking at the Apollo data, Hartman and Davis concluded that this is probably the best theory put forward. And by 1984, 10 years later, okay, so 10 years of more study and debate and everything else, this was the accepted hypothesis for the formation of the moon. Okay. So from the Apollo sample evidence, the moon was once molten to a very substantial depth, and it was determined that much more energy than that of accretion would be needed to do that. Something like an impact would create enough energy to make the surface molten, that deeply. We also find that the moon's surface is depleted of volatile organic compounds, which were likely to be burned off during a huge impact with all of that energy. And stable isotope ratios, namely oxygen and titanium, are almost identical to that of Earth, which will tell you that it was pieces of Earth that was knocked off and formed part of the moon. There are lots of other, there is other evidence as well. We look at the moon as being much less dense than the Earth, and a significantly smaller iron core. So the theory states that about a Mars-sized body, collided with the proto-Earth, and when it hit, most of the Mars-sized body coming in was almost completely destroyed. Okay, and its core was taken in mostly by the Earth, and that's why the moon has a smaller iron core today. Okay, and the density has to do with the determination there is that the Earth's magma that was forced out during the collision created and coalesced into these moon rocks. There's also a very high angular momentum. So in other words, the spin of the moon, the spin of the Earth, and the revolution of the moon around the Earth is much faster and much higher than other terrestrial bodies that we see in the solar system. So that energy had to come from somewhere. And they feel that a collision of such a magnitude would provide that energy to explain these high angular momentums that we see only in the Earth-Moon system. And also, the Earth's span and the Moon's orbit have similar orientation. And it's also believed that our tilted axis, our 23-degree tilted axis, is because of this collision. So think about the Earth could be a very different place without that. I mean, that's the reason we have the seasons that we have, right? It's because of that tilt in the Earth's axis. So these, even since 1984, since it's been accepted, okay, it's been 40 years, right? There have been many amendments, many derivative theories, as more scientific evidence is collected, this continues to evolve, okay? But nothing has pushed us away from this explanation of the creation of the moon that was created from a collision. So there's, about 50 years of evidence collecting that this is the way it happened. Like I said, there's some variation in the details and how it actually happened, but this is what we're going with now, right? This is our story, and we're sticking to it. Okay, so that kind of just brings me to the end. Like I said, I just wanted to tell you a story, maybe learn something. Maybe next time your daughter, or grandchild, or niece asks you, where did the moon come from? You can tell them, right? Big collision, bang. Question.
Hi, Michael. I just wanted to add to that. So some of the reading I've done is that, well, one, this particular theory is being challenged now due to new evidence, as you're saying. Also, too, I guess there's a big debate as to the impact of which they named there.
Right.
Was it a direct impact on the Earth? Was it, direct impact, or was it a glancing blow?
Glancing blow. Yes, I read some of that.
On that. And there's also something else where they're coming out with a theory about having more than one moon around the Earth.
Yes.
Not just one, but they could have been two.
Yep.
That then came together.
Yeah. And there was another alternate theory that the collision wasn't one body, but many bodies of more intermediate size that could have hit in a number of places, a number of times, and created that halo of rock that eventually coalesced into the moon. So yeah, and those are all the ones you mentioned, Ron, are all fairly recent. Those are in the 2011, 2013, so they're fairly recent developments that have been happening. Thanks, Ron. Any other questions or comments, or you're probably sick of hearing me talk by now, right? Hogging the meeting. Okay, with that, I'll turn it over to Steve. Thank you. We're talking about more practical matters.
I know it's getting a little late, but this is very short. Now that you've learned about where the moon probably came from, I want to show you a couple of things that you can look for. They're sort of easy, but they're sort of not.
Hold on for a second.
That one, top one. I'll do that. Okay, we're going to start with a blank screen. And then, okay, so we're going to hunt for an X on the moon and also a V at the same time. The interesting thing about these things, the X and the V on the moon, so-called, is that they're very easy to see, but for some reason, and some of you who have been around doing this as long as I have, may also have experienced this, I never learned about going out and looking for them until within the last 5 to 10 years. I didn't even realize that these were things that you could look for. They are short-term effects that happen around the first quarter, but you have to be able to look at the moon at the right time within a few hours of when the predicted time is. Anybody else that didn't know they were available to look at and just started looking at them within the last few years? Anybody else see them? Only 1 or 2 people. Okay. Well, the Lunar X and V, they are so-called clair obscure effects on the moon. And that's French for clair, for light and shadow. And it's used here to mean any effect on the moon's surface created by the interplay of light and shadow. These are not real features, but they are interesting things that you can see caused by light and shadow, which happens as The moon is illuminated bit by the rising sun over the course of each month. So the Lunar X, it's visible for a few hours around first quarter. It's a light and shadow interplay when sunlight illuminates the rims of the craters Lacaille, Longinus, and Purbach. I'm not sure if I'm pronouncing them correctly, but there they are. So let's take a closer look at these three craters. This is full illumination with the sun shining straight on. And you've got Purbach on the left there, Lacaille up on the upper right, and Longinus in the middle. If you can kind of see here, you can almost see a little X. You see that? That's what's going to be illuminated when the sun is at just the right angle. And as you can see, it's not an actual crater, not a mountain chain or anything like that. These are some pictures that I took last March of the Lunar X. And you can see right here.
Oh, yeah.
And it's actually quite a bit more noticeable when you're looking through a telescope. And this is a kind of a close-up. You can see it, but it's a very distinct feature. And it's caused by the illumination of the sun just hitting the tops of these areas between these three craters. And this is the Lunar V. And you can see that it's a very distinct V. This is a close-up. And this is not one of my pictures, but you can see here a little better illustration of what they look like when you're looking through a telescope. You can use a telescope of about 2-inch aperture or more to see these. And it's very easy to see. There's a little bit of a close-up on the left there. And it's not something you're going to see in first quarter unless you're within a few hours of the predicted times. So that's why I think it's not something that people really kind of recognize as something to look for until fairly recently. The Lunar V is due to elevated relief features close to the crater Euclid. And this is a view with full illumination. So, Euclid. And this is upside down from the last picture, but this is the V shape through here. And you can see the crater is there. You can see that when you're looking through a telescope at the V, and you'll be able to see the crater. But you can see that that is a kind of a distinct V shape. So when will you be able to search for these features in the future? If you go to this website, and if you Google Lunar X predictions 2022, you'll get taken to one of these prediction sheets. This is from Phil Harrington. Some of you may know him. He's spoken to us before, and he's written a number of books, but he's got a prediction out till 2023, and it gives the dates. So it's March 20th, 2148. This is in what's called universal time. And universal time, you can actually just Google convert daylight savings time to universal time, and it'll tell you exactly what these numbers are. And for example, on June 6th, the opportunity turns out to be at 5:20 p.m. local time. There's a window of a few hours around 5:20, maybe a couple of hours before, a couple of hours past it, but 5:20 is kind of the peak, and you want to be able to go out and take a look for these features then.
Are they both visible at the same?
Are they both visible at the same time? Yes, they are at the same time, which makes it fun and interesting to see them. So are there other clear, obscure objects to hunt for on the moon? Yes, as it turns out. There are just a few examples: Zeno Steps, O'Neill's Bridge, Grunheisen's Lunar City, the Buzzsaw, and many more. I haven't actually looked for any of these yet. I think I might try some, but if you want to see where some more are, you can go to this website. If you look up clear, obscure features on the moon, if you Google something like that, you will get taken to this wiki page, Wiki Moon, which will give you a whole big page of these different features, where they are, what quadrants of the moon they are. It'll help you identify some of them, so you can try to look for some of them. Some of them are a little obscure. They're not that distinct, but some of them are, like the X and the V, pretty easy to spot. So that's another challenge. And that's all I have. I just wanted to kind of show you that because it's a little different than just looking at some of the pictures. Yes, Lloyd? They should be visible during the daytime. If the moon, I mean, you can, the moon you can see during the daytime. It won't be quite as distinct as it is at night. It'll get a little washed out, but you should be able to see them. And I would certainly try it because if you look at that chart, if you convert the times on that chart, a lot of them are like 2 o'clock in the morning, 3 o'clock in the morning, times when it's not really convenient. This year does not happen to have a lot of really convenient times on the different months to see those. So if you want to try to see them, you have to make a little bit more of an effort. But you know, you can still try going out in the evening. And just when it's darker, you definitely see them, you know, quite a bit more brightly. Yeah.
I guess the next opportunity during the day to see it is around it's a date in April.
It was yesterday.
Oh.
I was out yesterday, inspired by our Lunar Observing program, just to give another push for it. I did take my telescope out and I looked. I saw the lunar V pretty distinctly. The X was starting to fade, but it was cloudy up until maybe about 8:30 last night at my house. So I couldn't go out any earlier. You could still see a little. You could definitely see the V. You could see where the X was. So you know, this is a range of times. It's not a specific time, and you're going to miss it. But you know, you can see a little bit before, a little after. But if at all possible, the ideal is, you know, when it's dark out and these features are bright, and but you can still see them at other times. Any other questions?
Are these presentations archived anywhere?
We have a YouTube channel, and we try to post these all on YouTube.
Thank you.
Anything? Yes?
Can I buy a vowel?
Oh, wow.
Letters of the moon, you know, we
Yeah.
need a vowel letter.
It's always one in a crowd.
Has anyone ever pointed out all the lunar O's up?
Not yet. That's after we get the award for the basic Lunar Observing Group, Astronomical League. That'll be our next project. So it is, I think, clear tonight. I think we'll be able to try to look at the moon. We won't see the Lunar X and V, but we definitely will get some good detail because first quarter is always great to see a lot of different features. Have another question? Yes.
For those, excuse me, for those people who are interested in conjunction, I talked to Jack Magus a couple of weeks ago, and he said the possibility of having this year, probably not.
Oh, really?
He's going to find out within a short period of time. Evidently, Northfield Mountain was sold, and he's having a heck of a time trying to get a hold of people.
What Russ is referring to is a lot of astronomy societies have conventions or gatherings during the course of the year. One of the ones that we've gone to for many years and would like to go to is called Conjunction, and it's been held in Northfield, Western Massachusetts, for many years. And it doesn't sound like it may happen this year.
That's what Jack was saying.
Unfortunately, but we will still have Astro Assembly in October, so definitely I'll come to that. Any other questions, comments, anything one up in astronomy events coming up that people want to mention? Please. Okay.